All right, what up, what up? Welcome to Jeremy season. Oh. So, everyone is building. The seeds are planted. The covenant's ready for activation. The community is locked in and building, and Jeremy season, I'm back. All right, so I've rebranded. I am working on Char, the Char Network, and we'll get into what that is. The TLDR is that it is a bonded Bitcoin consensus staking system. That system is going to build a BitVM reducer, so it's going to load state from that. That's going to help us build Bitcoin layer 2s for scale and functionality, and it's going to give incentives for our operators. This talk today, I want to put the spotlight on Attestation chain bonding protocol. This is a primitive that is useful in Char, and it's something that's a unique differentiator versus what other folks are working on in the BitVM ecosystem. And it's something that you also may have use for in protocols that you're working on as well. So what is an attestation chain? And we're going to give an example here with regular lease renewal, and that requires no changes or trust assumptions on Bitcoin. So at the bottom here, you have a series of messages that you want to sign. And this is maybe messages from any participant on a protocol that you're working on. Maybe it's BitVM, or maybe it's a CoinJoin, maybe it's a Lightning channel. And you have some first message and a subsequent message, a message after. And there's a sequence of these messages. Each message commits to what the previous message was. If at any point somebody signs two messages, those are able to be read in the system, and a key is able to be leaked out. So if you ever sign two conflicting statements when you're negotiating with a peer, you reveal a secret, and then that secret can be tied to a contract. That contract is a Bitcoin output living on chain, and that collateral has two outcomes. Either there's cheating and the funds can be burned, or after some amount of time, it can be redeemed, and maybe if you want to, you can renew the contract as well. If you are honest, there's no penalty. Now, if there were to be, and we heard in the last sessions a bit about covenants, if there were to be covenants, you'd be able to do this in a slightly nicer way. Rather than having to renew the lease regularly, you could just leave it sitting, and you'd only ever have to wait for redemption for 2 weeks before you're able to pull the money out. So let's look a little bit closer, because that was just a high-level overview at what exactly these attestation chains are doing. So in looking at these diagrams, arrows point backwards. You should read them as B commits to A, because B is happening after A. B points to A. And the arrows are owned by that chain directly. So the signed statement is using the knots that is in the previous message. That's the key idea behind bonded Oracle attestation chains, is when you sign a message, you also commit to the next thing that you're going to sign. These messages, by the way, this is just kind of like, you can think of it like Nostr with a couple extra features. So, and the red arrows are references to anything else. So if I am producing an attestation chain and you are producing an attestation chain, I can actually acknowledge, and this is something that you'll also see in, for example, a Nostr protocol, you can tag other messages that you're either replying to or that you've seen when you sent that message, and that gives you a strict ordering on your message came after. So you have here, you can see that one attestation chain is committing to the other, and then the other at some time in the future commits to that. So you get an ordering that you're able to establish over those. By, when you stretch it out, you can see that there's, okay, one arrow has to come after the other because it commits to it. It had to have known about that. Now, when you're scaling with many users, you start linking together, and you get kind of this braided infrastructure between all participants. And that scales across many different attestation chains. When cheating occurs, every participant is able to look backwards from their view to try to see what messages are available. And when a new message is conflicting, that helps bubble to the surface that there was misbehavior. And there can be multiple paths to prove out when a participant has cheated and signed conflicting messages. So when you use a relay system that is using these attestation chains, this is really beneficial for you to be able to deconflict and figure out if somebody has given you a false message, because there's incentive. If somebody learns that false message, the bond will get burned. You'll see that as an on-chain event. And that ends up being a critical, the critical feature of these attestation chains. Everybody has an incentive to try to burn. So another interesting facet of these attestation chains is around denial of service protection. In things like Nostr right now, you can kind of flood the network with a lot of messages, and that can lead to maybe some type of abuse. And if you have a network that you don't want to have spam on, because you don't want people just sending messages willy-nilly, you can add a time commitment to every message. So there are two key ways of doing this. One is to just say that you can only sign a certain number of messages per Bitcoin block header. So let's say that you can only sign one message per Bitcoin block header. If you then try to include that one twice, you can automatically reject it. Or if you try to equivocate, you would lose your bond anyways, and you could ignore messages from that signer. Or maybe a more interesting way is to use a stateless verifiable delay function to guarantee that messages take a certain amount of time to generate afterwards. This is not something that I personally invented, but just giving you a little bit of context on it. It's basically equivalent to saying that when you generate a message, you have to run a very long proof of work on it. So maybe like a proof of work that would contain 10 minutes of effort. But it's not the same as proof of work, because proof of work is randomized. You have a nonce that you're grinding, and it means that it's parallelizable. A VDF has a fixed argument that's going in, and you just need to do the work. The problem with this type of VDF is that the verification process takes as long as the proof generation process, because you have to yourself run all the hashes. In order to resolve that, you can add a zero-knowledge proof basically over that chain of hashing. There are a couple different ways of producing these VDFs. This is just one general technique. And then you say, I proved that I did this hash function 1,000,000 times, and that took me, let's say that takes about 10 minutes. You can give that proof. Somebody can check that in a one constant time operation. So you can dial in the amount of work. And if you include these VDFs in every message that you're signing along the attestation chain, then you are able to basically say you could sign one message every 10 minutes, one message every week, and then that can be in a system that you're trying to build peer-to-peer consensus. You can rate limit how participants are interoperating. So you wouldn't be able to have a valid proof time, or you'd cause a conflict. So unfortunately, I think my slides did not update. There's a little bit more, but what I'm going to tell you about is how this impacts Char and the research and development that I'm doing. So in protocols like BitVM, there are two main roles that people play. There's the prover and the verifier. There's also the user. So the user is not necessarily a verifier or a prover. Just to use one of the systems, you don't have to do the verification. You should, but maybe you think that this is a very widely used network and you're happy to see other people doing the verification. You think that they have enough economic incentive to do that. Every prover and verifier, they issue and respond to challenges in that system, and the prime way that they do that today is through an on-chain interaction that is set up of, I'm going to challenge you on this or on that. However, in brokering when someone should challenge or not, one of the weird issues is that one party communicating to the other may not send the same message to everyone. And if you don't send the same message, you might be able to convince someone that they should be okay and satisfied, but then you send somebody else a different message. Those two things existing in conflict until you see the on-chain resolution may lead to a negative outcome for you. So if all of those parties are using these bonded Oracle attestation chains, then everybody participating knows that if the prover or the verifier has communicated duplicitously, then they are going to actually face an economic penalty. And that can help in these systems. One, that economic penalty disincentivizes, but also gives everybody else the incentive to inflict the punishment on them. So that combination of incentives can help align the operation of these networks. And you can also take from these attestation chains, reading the data, you're able to create an argument pack of what you actually apply to the BitVM state machine. Where are the arguments of BitVM coming from? What are the accounts that people are running? One of the issues in a protocol like Ethereum, for example, is that when you do a transaction, you can race in the mempool to sign multiple conflicting transactions. And then there's a mempool of like, OK, well, what if you replaced it with this other one? Should that go in or should this other one? In a system using a bonded Oracle attestation chain, you can say, look, do your transaction, but you can't replace it. Once you've issued this, the network has to incorporate it. And if you want to countersign, you're actually going to cause other participants to be able to steal or burn out all your funds from the network. So it creates a powerful network of incentives for honest participation. I mean, it's maybe irrational at this point, but honest participation, which can dramatically simplify the architecture that you have to build around one of these BitVM ecosystems to get a fully functioning layer 2. So that's sort of the core concepts behind what's becoming the Char network. Char is going to be a BitVM layer itself that is using this as a consensus orchestration system and user account system. But this is also a general technique that will be available as sort of like modular sequencing to other layers that are trying to figure out how they're going to solve this problem as well. So that's the bulk of what's going on here. Because we're in Jeremy season, what I will say is covenants are happening. It seems like there is technical consensus. It's just really, I got to say, you're not going to see it from me. I'm not launching a client. I'm not putting that out. I'm focused on this. It's up to you guys to have the debate, the discussion, to drive it forward and bring that home. But I'm glad to see that everybody is on the train, and we'll get some cool stuff to happen. Thank you very much. I guess I have time for a question or two. I don't know. Usually open source stages take questions if anybody wants to grill me. All right, I'll call it at that. You'll find me afterwards. I've got some keychains for y'all, and you'll definitely want one.